All right, we're going to walk through a little numerical example of a socially optimal versus market equilibrium in the presence of an externality. The example scenario here, we have the supply and demand information for pistol ammunition. Right? So what we're going for here obviously is going to be a negative consumption externality. But before we get to that part, let's kind of break down what we have in the table. Typically, when we had seen supply and demand tables before, there would be one column with the price, and then the supply curve would be based on the relationship between quantity supplied and that price, the demand curve, quantity demanded, and that price. Here, what we see is one column with our quantity values and then the associated height of the supply curve versus the demand curve. So our marginal private cost column here, that's going to be the height of the supply curve. The marginal private benefit is the height of the demand curve, the willingness to pay of the consumer. The first part of the question just asked us to find the equilibrium point and show it on the diagram, and that'll be the intersection of private cost and private benefit. And we see very quickly that that's going to occur at an equilibrium quantity, QE of 4,000, when the private cost and the private benefit are both at 20. So we can sketch that out real quick. So the demand curve, that is our marginal private benefit. Our supply curve, marginal private cost. And our equilibrium point, quantity of 4,000 QE, and equilibrium price at $20 per unit. So now, for part B, enter in the externality, right? So suppose we can calculate that there is an external benefit of negative $8 per unit, right? So we're imagining that captures the increased probability of an accidental shooting, increased propensity for violence, etc., when there's more ammunition floating around. What we're constructing here is the gap between the social demand curve, which is our marginal social benefit, and the private demand curve, the marginal private benefit. So numerically, right, all we have to do is add the external benefit to the private benefit, which in this case is going to be subtracting the $8, right? So we subtract 8 from the height of the demand curve, the private benefit, to get the social benefit. So 26 minus 8, 18, 24 minus 8, 16, and so forth. 14, 12, 10, and 8. So what we're going to do now is show the marginal social benefit curve, a parallel shift downward relative to that private benefit. And the intersection here is going to give us the socially optimal level of output, the Q star. So part of the trick here is recognizing that we're not mentioning any externality on the supply side, right? So the private cost, the marginal private cost, and the marginal social cost are going to be the same, right? So there's only one supply curve that we have to deal with here. So what we have to do is find the intersection between our social cost and our social benefit, and that's why it's always a good idea to start with the graph, right? Because we know, just like any case of a negative externality, the socially optimal output will be lower than what the market is doing. So we have a good spot to start looking. So the original quantity was 4,000, so we go down from there. At 3,000, we have a social cost of 18, a social benefit of 14, so that's not it. At 2,000, marginal social cost and marginal social benefit are both at 16, so that's where the two intersect, so that's going to be our Q star level, and we could put that on the graph there at 2,000, and that new equilibrium, sorry, not equilibrium, the dollar value at the socially optimal quantity is going to be that value of 16. We will label that properly in a second. So now we have the externality situation, and again, we can label the vertical distance between our two curves here. That's the external benefit. That's the -8 shift down. And now part C asks us about the appropriate Pigouvian remedy for the externality. Right? So we know that it's a negative externality, so there's going to be a tax imposed to discourage the activity, and we know that the externality is coming from the consumption side of the market, so it's going to be a tax imposed on the consumer of the good, and the value of the tax needs to match the value of the externality. So what's going to happen is that our after-tax demand curve is going to exactly equal the marginal social benefit. Right? When we impose a tax on consumers, it reduces that willingness to pay by the value of the tax. And if we can set a tax equal to the value of the externality, then we'll essentially have two lines right on top of each other, the after-tax demand and the marginal social benefit. So the quantity after the tax will just equal Q star. And now we can start thinking about the price levels, right? Remember, anytime there is a per unit excise tax imposed on a good, it's going to drive a wedge, as it were, in between the prices paid by the consumer versus the price received by the seller. So the lower price level of 16, that is the after-tax price that the seller gets to keep, right? The amount that the consumer actually pays, what we would label the PC, includes the value of the tax, right? So we have to go back up by the value of the tax, in this case, the $8. So the consumer pays 24 after the tax, 8 of that goes to the government, and the seller gets to keep the 16. So that's where we get the question of the burden of this tax, right? So just as we've seen in the past, the tax burden is going to be measuring the losses to the two sides of the market, right? So for the consumer burden, we're tracking how much more they end up paying because of the tax. So now they are paying 24, they used to pay 20, and they're purchasing those 2,000 units, so $4 per unit. So that'll be an extra 8,000 that they have to pay. That's their burden of the tax. In this case, it turns out to be exactly symmetric, right? Because the revenue loss for the seller is also going to be the $4 per unit, right? They used to receive $20 at the old equilibrium. Now they only get to keep 16, so they're losing $4 per unit, and again, selling still those 2,000 units. So they have a burden of 8,000 as well. Okay. So now the last question, explain why, unlike in many cases, i.e. any case without an externality, there will not be a deadweight loss due to this tax. So what makes this a special case is that the tax is imposed exactly to counteract the deadweight loss coming from the externality. Right? So go back to the pre-tax situation when the market was producing QE above that Q star level. Each unit produced above Q star, right, had a cost to society on that social cost curve greater than the benefit to society, right, the value along the social benefit curve. So for each one of those units produced and sold at the old equilibrium, there was a net loss. Right? So that area is the deadweight loss due to the externality, right? Due to QE being greater than Q star. So rather than causing a deadweight loss, this tax erases the deadweight loss due to the externality. Right? that's what makes this, in that sense, an optimal policy rather than an inefficient policy. So hopefully that was clear and that was helpful. The main thing is know how to fill out the table, find the QE and the Q star, recommend the Pigouvian remedy for the given situation. Not a bad idea if you wanted to play around with the numbers, say, well, what would happen if there was a positive consumption externality of $8 or a negative or positive consumption or production externality of $8? Make up your own scenario. It should work with these numbers, and make sure you can draw the graph that matches the given situation.